Muchas gracias por su asistencia. La plática fue una oportunidad, sobre todo para que ustedes, estudiantes de la maestría en Administración en el ambiente, puedan percibir cómo se explora de una manera más técnica un estudio. El doctor Weiss accedió amablemente a darnos una plática. Me gustaría presentarlo después de una sesión de 45 minutos. Vendrá aquí y tendremos una sesión en principio de 15 minutos de preguntas y respuestas. La presentación va a ser en inglés y me gustaría presentarles al doctor Weiss. El doctor Dominik Weiss estudió química en el ETH de Zúrich, donde se graduó en 1993. 2 años después trabaja en laboratorios de investigación para el sector industrial en Novartis y académico en el Weizmann Institute of Berna, de Science de la Universidad de Basel. En 1996 ingresa a la Universidad de Berna para estudiar un doctorado en Ciencias de la Tierra, el cual obtiene con honores en 1998, al defender un tema de tesis sobre geoquímica atmosférica del plomo. Después, por 1 año y medio, desarrolla un postdoctorado en el Departamento de Oceanografía Química del MIT. En 2000 es contratado como un investigador en geoquímica ambiental en Imperial College London, es ahí donde nos conocemos. En 2005 es promovido a Senior Lecturer ahí mismo. Ahora es un investigador asociado también al Museo de Historia Natural, the Natural History Museum en Londres, donde coordina los laboratorios de espectrometría de masa y geoquímica isotópica. Esta infraestructura está compartida en lo que es Imperial College y el Natural History Museum. Ha sido profesor visitante en el Departamento de la Universidad de Xiamen en China, en la École Normale Supérieure de Lyon, en Francia, en la Universidad de Sao Paulo, Brasil. Actualmente se encuentra en una estancia sabática en la Universidad de Stanford. Y bueno, Dr. Weiss, es un placer tenerlo aquí. Thank you very much, Dominik. So, you can start.
Okay, thank you very much. Up to me to say thank you for being here. So I will talk. Does everyone understand me? Yes. Okay. I speak a little bit Spanish. So if there's any questions, maybe it's not clear, then try maybe
You have to use the app because
a microphone, if you need it.
Okay. It gets complicated. Okay. Okay, so I will talk about kind of the work which we've been doing for a while now at Imperial College and now at Stanford on the understanding the effects of human activities, especially on the atmospheric metal cycles. And okay, first of all, what kind of drives our motivation or why we're interested in? There are 2 distinct points which I want to emphasize. First of all, there is the important effect on human health. So metals in the atmosphere, so once we take the metals up and it reaches, for example, our lungs, then there is oxidative stress for elements like copper and zinc. There's also an impairment of the neurological development in the case of lead. And we know that in a lot of big cities in the world, there are still the concentrations in the atmosphere and consequently also in the blood of people are far too high. An example is still for example, in Mexico City, where lead concentrations of children are often still too high and likely affect neurological development. But there is also an interest in terms of from an Earth system perspective. And the reason is there that basically if we transport, for example, dust in the atmosphere, deposited in remote ecosystems like the open ocean or the Amazon basin, then we basically are fertilizing, or there's basically a way of fertilizing these ecosystems. And for both, on one hand, obviously to develop proper policies, on the other hand, to understand the functioning of the Earth system properly, we need basically to know where do the element comes from and how much do they come from. Okay? And that's basically the work which we are mainly involved at Imperial College. The tools which we use, one of the main tools is that we use isotope ratios. So now I'm not familiar how many people of you know about isotopes and isotope ratios, but ultimately it's basically just that we use for different elements, different isotopes, and look at the ratios of them. It's ultimately something like looking at, it gives to an element like a color. So wherever the element comes from, it might have different colors. And the advantage of the isotope ratios is that compared to other techniques is that normally it allows us to identify and quantify sources which often elemental concentration, for example, don't do successfully. Here you see, for example, the zinc-cadmium isotope concentration ratio in different geochemical reservoirs, and you see the variation is much larger than in terms of for the different reservoirs than we often have for the isotope ratios, and therefore it's actually often not that a good proxy to study the sources. It also helps us to identify environmental processes. I don't want to talk about that in more detail, but because isotopic fractionation helps us to understand what kind of chemical processes happen in the environment. And the big advantage is also that isotope ratios, if we use ratios, we can be much more precise in the measurements than we can do with concentration measurements. Okay, so we are order of magnitude more precise, and you will see afterwards how important that is. The types of isotope systems which we are using are so-called radiogenic and non-radiogenic isotope systems. A typical radiogenic isotope system is lead, and that means the isotopes of lead, for example 204, 206, 207 and 208, these isotopes are constructed or basically are formed by the radioactive decay of uranium and thorium. And depending on the decay constant, depending on the age of the lead, okay, we have here the age of the Earth, we have here the different isotopic ratios. So depending on the different decay constant, at a different time when the lead was formed, we have different isotopic composition. So therefore, that leads to an isotopic variability of lead in the environment. There are non-radiogenic isotopes. These don't have radiogenic parent nuclides, and there we find isotopic fractionation through chemical processes, biological and physical processes. And what you see here, that's just as an example, there is the isotopic composition of zinc. It's expressed not in absolute ratio, but in relative ratios. It doesn't matter too much exactly how we do that, but let's say just that's the relative ratios. And you see there are chemical and physical processes which lead to distinct isotopic fractionation and therefore to a distinct isotopic signature in the different reservoirs. Okay, and once we have these isotopes determined in the different sources, for example, different geochemical reservoirs, then we can use them like colors to identify in a sink, okay, so different sources, and then in a sink setting we can identify where actually the sources come from, and we can calculate the contributions. So here that are just obviously if we have two different sources, that we can do a two-component mixing. Two-component mixing means that we need at least two equations if we have two unknowns. If we have a system with three different sources, we need at least three different equations to solve the problem. But anyway, the important thing is that we can use isotopes to identify the sources, and once we know the sources and the isotopic ratios, we can start to calculate the contributions of the different sources using simple linear equations. Now to measure the isotopes, that's ultimately probably the specialty which we do arguably at Imperial College. And my background itself, it's actually being an analytical chemist, so I did a lot of mass spectrometry. And here that's just a schematic of mass spectrometer which we use And you see here, that's basically the plasma source where we ionize the element, and it goes through the instrument, and then we separate the isotopes. Okay? And that we can ionize the element and we can measure the isotopes at exactly the same time leads that we have a very high increased precision. Okay, so on our isotope ratio we get precisions of about 0.02%. That's because we have a multi-collection. If we do single collection, which normally used with quadrupole instruments, it doesn't matter so much, but it's a more popular instrument in analytical laboratories, we only get about precision of 0.2, and the consequences of that I will discuss a little bit more in detail afterwards. Okay, so I think that's the most important for this slide. As I said, we're talking about the precision, and just to show you the importance of the precision, for example, in environmental studies. What you see here, that we did a study in Siberia, no, sorry, that was in the Urals, where we had basically, we were interested in the dispersal of toxic element around the smelter. So what you see here, there's the smelter, and then we collected lichens along a transect, okay, so that's here the transect of the valley. So we went from north to south, collected lichens, measured the lead concentrations, and what you see, so here that's where the smelter would be, okay, and what you see is basically what you would expect, close to the smelter, a lot of lead, and as you go further away to the north and to the south, the concentrations are decreasing. So that's a typical kind of Gaussian curve, and probably every one of you would say, okay, that's basically nothing else than the dispersal pattern of the smelter lead. Now, if you look at the isotopic composition, then we actually see that that's not true. You see here, that's that's where the chimney is, okay, so that's the smelter. Sorry, I think I'm losing the light. Ah, that's good. It's okay, that's stupid. Okay, sorry about that. Okay. Okay, so that's the isotopic composition now of our source, so the chimney dust, okay? That's the concentration of the lead, and if we plot the isotopic ratios versus the inverse of the concentration, then we get basically, if we have a straight line, then we get the mixing line. And the key point is now that are all the lichens along the transect in the north. You see here the isotopic composition, even if we are far away, is exactly the same like we have in the chimney dust. But when we go here, then we see the isotopic composition of this lichen here is not the same isotopic composition with here. And that tells us that the source of this lead is different than that. This source is definitely from the chimney, but here it must be another source. What you see here also, that's the error bar on our measurements. So because we are so precise, we can definitely say this point is different from this point is different from this point, and clearly what we would from concentration data alone, we would identify that as one source which disperses, but here clearly we can show that there are actually different, at least 3 different sources in our system, or 2 different sources, a natural background, the chimney, and here there's the same chimney dust. Talking about precision, and again, that's something which probably more for people of you who worked with mass spectrometers are maybe can appreciate. Because now we are so precise, we can measure isotope elements like zinc or copper to such a high precision that we can actually identify isotopic variability. So here that's the zinc variability in different rocks, sulfides, sphalerite, different minerals. And you see the isotope, we can now, depending where the zinc comes from, if it comes from ores or if it comes from carbonate rocks or silicate rocks, we see have a different isotopic composition. And now, because we are so precise, we can say this zinc here is definitely different with the isotopic composition than this zinc here. Before the the development of this type of mass spectrometers where we can measure the isotopes all at the same time, this resolution was simply not possible. Now it is possible. I think I will jump over this, that's a little bit more technical, and we'll go directly to one of the big interests which we have, is to understand, when did actually pollution start on a global scale, and how much do we actually pollute the system? Why is there the interest in identifying the start of the pollution? If you see here, that's the enrichment factor of different toxic trace elements in atmospheric emission of natural versus anthropogenic over natural. And we see, if we look at atmospheric emission, the different anthropogenic sources and human sources, we see that we have lead, for example, is by far dominated by anthropogenic emissions. Well, what are the consequences? If you look here, that's just simply the distribution pattern or the atmospheric pattern of the circulation, and you see that basically air parcel which leaves here the United States within 2 weeks actually arrives in China. It's a little bit more difficult to get from north to south, but you see there is basically important in a short time the pollutants can travel a long way. So we are interested in understanding how far does pollution go and when did it actually start, because clearly, because we have polluted the atmosphere so much already, it's difficult from nowadays data measuring aerosols. Nowadays, we basically can't find out where it actually comes from or when it started. And the way we study these aerosols is when we look at present day pollution. We, on one hand, we just use active aerosol samplers. That's just a system which we used in a recent study in Sao Paulo. If we want to cover large geographical area, then obviously it's impossible to put everywhere active samplers. What we then use is so-called passive sampler systems. In that case, that's here again the study of the smelter study, which we used in the Urals, where, as I said, we used lichens, so that is plants which are growing on trees, and we basically collect them and use them as atmospheric deposition filters. If we want to go into the geological past, what we then use, we use geological archives. In that case here, we have a peat core, and we see here, a peat core is nothing else than an accumulation of organic matter, which basically represents an accumulation of atmospheric deposition, and then we can identify where the metals come from and what they do. And that was probably that was a result of my PhD thesis, where I was interested in using a peat core, which you see here, that's a depth of the core, so that's the same like a soil, okay, so like a soil profile. So you have a depth profile. We were looking at all atmospheric deposition, and we looked first at the lead concentration, and we wanted to know when did actually pollution start and where does it come from. What you see here is the lead enrichment factor, so that's basically just normalized to the background, and here the isotopic composition. And I don't want to go into many details, but what you see is basically at a certain depth, so there's a different scale, please note that, at a different scale, depth, there's once of a sudden about 100 centimeters, a huge increase of lead, and clearly this lead seems to be from a different source. And if you look at the isotopic composition, that's the isotopic composition, we see that's kind of a natural isotopic composition of lead in dust, and once the concentration is increasing, then also the isotopic composition is changing, and this lead here has an isotopic composition which can't be explained as natural dust, and this lead must come from ore. So we basically can here identify and show that 3,000 years before present, in Europe, mining started to be a very important, at least regional scale activity which polluted the atmosphere. And obviously in recent time that has become only worse. So here that's the Industrial Revolution which is reflected. Here you see the use of gasoline, and what you see here is basically the decrease of atmospheric lead is due to the decrease of, or the not use of leaded gasoline anymore. And you see that's also reflected in the isotopic composition. That's the gasoline lead. It has a distinct different isotopic composition than the industrial lead, which obviously has been driven by coal, that has an isotopic composition in this area. And you see, once the lead actually goes back, then we also have a change in the isotopic composition again. And given that the atmospheric transport is so important, so we started to look and were interested, well, let's have a look how far does actually this lead get transported. And what you see here is that we went then to the Faroe Islands, so that's in the Arctic, and took a peat core there as well, measured mercury and lead concentration, and what we see again is there is actually an increase in the top part of the soil of lead, okay, because we can age date this soil, so that's the age date of the soil, okay. We see actually that the increase or the highest concentrations of this mercury were actually not present day, but they were in the 1950s. And if we look at the isotopic composition of the lead, then we see that it's a distinct isotopic composition, which is typically for coal. So we can say that the peak in 1950 in the Faroe Islands comes actually from coal combustion, and the very, very recent lead is actually, there's no high concentrations of lead in the very recent time. So it seems that actually the gasoline lead hasn't affected the Faroe Islands as much actually as coal combustion did in the 1950s. I think I will jump over that, but we were also kind of looked for a while then if a similar effect we can see in the Chinese rise of civilization. So when you think here, we see here basically the start of the Roman mining. We were interested if we can see a similar effect of the Chinese civilization. Again, we looked at the peat core in the middle of the Tibet, looked at the depth here, and that's the isotopic composition, and that's the isotopic composition, and that's the lead enrichment. And I don't want to go in too much detail, but basically we don't see the same. Yeah, we don't see here exactly. So we see here again changes in the isotopic composition. And first we thought, wow, maybe we can actually see here also that's approximately 3,000 years before present. So we thought first, well, maybe we can show here that actually that's an effect of the Chinese civilization, because people using lake sediments here in the middle of China actually found evidence of Chinese mining up to 7,000 years before present. But we were, as I said, more far away. We were in the Tibet, and we see here changes in the isotopic composition, but the changes are not big enough to explain it with lead coming from mining. So we have changes in isotopic composition of the lead, but compared to what we see here in Europe, okay, where it's so strong, this isotopic shift, we don't see the same strength or magnitude of shift for the lead, and clearly that probably suggests that this lead here comes from natural sources. And indeed, when we then did a little more detailed assessment of this core, used some more trace elements, rare earth elements, and so on, and analyzed these peaks a little bit better, then we actually could show that we can explain these changes in the lead due to different source changes in the atmospheric circulation within China, and simply different dust sources arrived here in the Tibetan plateau. But this idea of showing that these lead isotopes actually give us an idea about atmospheric sources and dust fluxes, and therefore changes in the atmospheric circulation, that's something we picked up. So we started to investigate the atmospheric lead record, the isotopic record in Europe from different peat cores and ice cores. So here that's the whole compilation of the whole world which we did. And what you see here is basically the isotopic composition in peats of different places in Europe, Sweden, France, Spain, and Switzerland. And what we then once of a sudden realized that you see here at about 2000 3,500 years before present, we see a distinct peak in the isotopic composition in all of the 4 cores, and that made us to suggest that we basically must have had about 4,000 years before present a significant volcanic event in Europe, which before we haven't really known that this one exists. So that's obviously more an excursion into the Earth system science, but you see we can use lead isotopes also for that very successfully. So I think I have another 10 minutes left, so I want to jump a little bit and show you about the present work which we are doing, or what we're interested in at the moment to work on at Imperial. And our main interest is now kind of has shifted, and that's also why we looked at China. We start to be interested kind of how much do now, I mean, we know that the Europe and North America, they started to put in, you know, very efficient emission controls. Okay, so the emissions, as we see here, for the lead, the emissions have gone back. Obviously, we see here from this plot still the concentrations are still elevated, but clearly the most developed countries, they don't have these high concentrations anymore. But if you look now on a global scale, what you see here, that's just anthropogenic NOx emissions, that you see that the regions which before were less developed economically now start to pick up very, very quickly. And when you see here, there are 2 really, I think, impressive tables and figures. So that's taken from Wikipedia, which shows the mega cities which we have in the world, the 10 biggest cities. And when you see here, Mexico City, Sao Paulo, Buenos Aires, Calcutta, Delhi, they all are all in places where we have emerging economies. So there's huge emissions of trace metals in the atmosphere to expect, and clearly we need to know what's the effect of them for the global environment. If you think the big affected anthropogenic emissions of the northern hemisphere in Europe and the North America had. Here, just to show you also, just specific for a few elements here, that's the emissions in ton per years, and you see here that's for copper and arsenic, and you see the overall. I mean, when you look at the copper, you see Asia and South America, they have overtaken by far North America and Europe with copper emission. Similar it is with the arsenic emissions here. South America, Asia have overcome by far North America and Europe. So if we want to understand global metal fluxes, atmospheric, clearly we have to shift our attention to the southern hemisphere. And just to make the point and of the most recent work which we did on lead, again, and maybe I take you kind of here through the different plots. First of all, here that's where we looked at the lead isotopic composition in the North Atlantic, measured in the at the beginning of the 80s, waters collected at the beginning of the 80s, and then at the end of the 80s. Here, that's the isotopic composition of the aerosols in Europe. Okay, that's a typical isotopic composition of aerosols in North America, and that's all the isotopic compositions measured in surface waters in the North Atlantic. And you clearly can see that's a nice mixing line between one end member, aerosols Europe, aerosols America. All the lead in the ocean basically comes between these 2 end members. Now, 10 years later, so if you remember in the 70s, 80s, America and Europe started to phase out the leaded gasoline. And when we did the same measurements, again here there are the major sources, isotopic composition in North Europe and in Europe and in North America. If you now look at the isotopic composition in the North Atlantic Ocean, you see that most of the samples still actually fit on a mixing line, but we have now a distinguished set of samples which are off this mixing line, and therefore there must be a different source of this lead. It can't be North America anymore, it can't be Europe anymore, and we haven't followed up that in more detail, but when you see here that are the samples which were just collected in the southern equatorial western North Atlantic, which is obviously close then to Mexico. And you see here that actually the different sources could be, well, that's influx of starting of Mexico contributing the lead pollution in the Northern Atlantic. A similar shift is shown here. Again, I want to take you through this plot a little bit more carefully. You see here what we measured were the isotopic composition in coal. Okay, that's what we measured. We collected different coals of different places in the world. You see the aerosols of isotopic composition measured in the aerosols. And we wanted to look how easily do they isotopic composition of coal and aerosols interlap. And you see for most regions of the world, the isotopic composition of the aerosol, lead in the aerosols and coal is different, which basically nothing else is because the major lead sources is still the gasoline lead. Recycled, probably places like Canada where it's recycled gasoline. But there are a few interesting things, and probably the most interesting point which I want to point out is here. If you look at China, you see here that's the isotopic composition of the coal in China, that's of the aerosols. Most of the lead in China, from our data, suggests comes actually from coal burning and not from gasoline anymore. And in addition, when you see here, the isotopic composition of the coal fits nicely with the isotopic composition of the aerosols measured in the US, in the western US, and that confirms or basically supports the suggestion that important influx of Chinese pollution from China emitted actually reached the US, the western US coast. You see here the aerosols in the eastern coast, and obviously there's a certain overlap, but otherwise it's quite distinct different. So we see clearly there is a change in the atmospheric pollution pattern globally happening, and that's something we want or are interested to understand a little bit more. So I have 5 minutes left, and then I'll stop, and maybe I just jump over this work, so where we looked at lead sources or maybe actually I should just probably finish off most easily with this plot here, where we're interested looking at where does the lead come in the atmosphere of Sao Paulo. And the major question there was kind of the increased use of biofuel. Is there any effect of biofuel on the lead concentrations in the atmosphere? And equally, if there is an important contributions from diesel and from gasoline fuel. And what you see here is basically just the isotopic composition of the aerosols, okay, which were collected in Sao Paulo. Again, we have the different end members, okay, so that's industrial lead. Here you see the fuel lead, and you see here the gasoline lead, okay. And you see that most of the isotopic, well, all of the isotopic composition we can explain with a mixture between the fuel lead and the industrial lead, so it lies nicely on a mixing line. But we have also an important effect of the, that's the alcohol fuel, and here of the gasoline fuel. So we have also an important impact on the gasoline fuel. And if we just take the samples which are on this mixing line, then it's basically two-component mixing line. That's what you see here. Then we can start to calculate, as I showed at the beginning, the different contributions of the sources. And if we look at the lead isotopic composition of the gasoline, here it's of the alcohol, then we calculate that we have approximately 70% of the lead in the atmosphere in Sao Paulo comes actually from gasoline and not from alcohol. So the biofuel doesn't seem to be a significant lead source, even though it was suggested, and still gasoline and industrial lead are a major source. And maybe to finish up here, a very interesting temporal study which we did in Sao Paulo as well. So you see here we measured high resolution, basically sampling over 4 days. what you see here, the isotopic composition, and you see that's the power of the isotopic composition. If you look at lead concentration, you just see that it's pretty much the same. You would argue, you know, there's kind of a background, the same source or whatever, there's background, and then you have a distinct event here. This distinct event we can explain very simple, because there was a big football game in Sao Paulo, and I think Sao Paulo won, and there was big celebrations. So there were big artificial fires, which are known to emit a lot of lead nitrates. So I think we can understand this peak very, very simply. But the interesting thing is, you see, if you look only at the concentration, you have no idea where this lead comes from. If we look at the isotopic composition, then we can say this lead here clearly has a different isotopic signature than this lead here. Okay, so that's the most dominated here by purely by gasoline. But here during that period, Friday, Saturday, Sunday, we have an increase of the contribution from the alcohol. And when we try to explain that, the most important plot is probably this one here, where we have the wind directions, and we clearly see here a strong change in the wind direction. Okay, so it's not necessarily actually the pattern or everything like at the place itself, but it's actually the wind pattern which transports the lead to the sampling site, which was at the University of Sao Paulo at USB, where we collected the aerosols. With the change of the atmospheric circulation, there is a change in the source of the lead. And again, without isotopic compositions, we wouldn't have been able to detect that. Okay, so I think, to be honest, that's where I stop. So I wanted to show you also the use of zinc and copper isotopes for source tracing, but I think that just would take us another half an hour, so I really want to jump over that and probably go straight to the conclusions, which we have here. So first of all, clearly we see that metals play a key role in atmospheric pollution, in atmospheric transport. We see that high precision isotope measurements enable us to accurately identify the sources and the processes. We also see that lead isotopes clearly show us there is an important impact of emerging economies on global environmental health. For example, it seems to suggest that there is important transboundary pollution coming from China affecting the USA, and as I said, there's kind of some evidences also that maybe Mexico might affect the environmental health of the open North American Ocean. As I haven't had time now to talk about zinc, maybe that's another time to talk about this one, or if you're interested, you can come and talk to me afterwards. But otherwise, that's it, basically.
Well, thank you very much, Dominik. So come on, don't be shy, come here, sit down, and then be prepared to be shut up by all the questions of my students that have been quite attentively following your talk. Come on, sit down. Thank you. Bueno, chicos, ¿preguntas? Si no, les vamos a empezar a preguntar nosotros a ustedes. Dani.
Dominik, is the active sampling the only way you can get the sample?
The active sampling?
Yeah.
It's just you have different information which you get. I mean, if you make active sampling, obviously you have a total control of the air volume which you're pumping, so you get basically a flux information. If you have passive sampling, you don't get flux information, you get only deposition information. You can say, you know, this and this amount of trace metals per square meter or something falls down, so you don't get a time information. That's the big difference. Depending, obviously, you know, what's your scientific question, you guess, you know, if you need time information and flux information, then the passive sampling doesn't help. Having said that, at certain places you're just limited. I mean, at the moment we are planning to do, looking at the dust fluxes into the Amazon forest, and we basically try to cover the whole of the Amazon, and, you know, it's impossible, obviously, you know, to have, you know, 50 samples which need pump and, you know, very careful people, you know, how to change these things. That's impossible. So there we just decided we take passive samples, just, you know, put them on the most, you know, important places and just collect them passively. We get then information about the sources, we get about the deposition rates, but we fluxes, but we don't. Sorry, fluxes, but we don't get about the rates, and that's obviously just a compromise you have to do.
Yeah, because Canada is leading a program, global atmospheric passive sampling.
Mm-hmm.
Have you heard about it?
No, to be no, it probably shows my ignorance. No, I do.
Yeah, and they are collecting, they are applying passive sampling. Puff, but the plate is like a little ovni.
Yeah.
And there is a little temperature sensor, and they have models that, with the temperature recorded in this sensor, they can calculate the flux.
Okay.
With the sampling. So I think it would be interesting.
Yeah, no, that would be nice to talk maybe afterwards. Yeah, no, that would be for us. I mean, I think that sounds. Yeah, no, that's. I mean, as I said, I mean, to admit my ignorance is that I just spent most of my time on the mass spectrometer, which
it's
that's
very
probably
difficult.
So I appreciate very much. You know, that would be very interesting to hear more about that. Yeah.
Okay. Yeah.
Thanks very much.
Jaime.
It's probably just if you would talk with people who do policies, that probably would help a lot. I practically, I really don't know. I mean, in terms of, I guess, the lead. I mean, definitely the lead story. You know, obviously that was before my time, but I guess it was really the work on lead which showed the isotopic work. You know, that the main source is gasoline, and consequently, people started to phase out, you know, leaded gasoline most over the world. So, you know, that has been one of the major you know, policy achievements, and, you know, politically quite interesting in terms of once people started to work with the isotopes, and the person who really pushed it, there was a Claire Patterson at Caltech, and I mean, he had, you know, plenty of lawsuits because the gasoline companies obviously didn't like what he found. So there is definitely direct impact, and I guess, but ultimately, I mean, my feeling is obviously often between, you know, source tracing. I think it's always, you know, what techniques you use, and I guess it's always. My understanding is actually to find a proxy which really pinpoints very clearly where it comes from. I think with lead we were very, very lucky. As I said, we kind of testing at the moment the potential of zinc and copper isotopes to look at high temperature processes and low temperature, I mean, sources. It seems to work, but less clear cut. And I guess with all these things is, you know, till it goes then into policy. I have no idea about policy, I do admit. And I guess it's all about, you know, how much, you know, you're sure what you say, you know what I mean, in terms of quantification, and you know, as a scientist, probably I would always say, well, you know, we think it's like that, but we are not sure, and then I guess policy people want to be sure. So I do really not know. I mean, I guess probably it's a question I should ask you, because probably you guys know much more about that than I know. So from that point of view, it's a very good question, but probably people would have to, yeah, to talk them more together. And, you know, surely, I mean, we would be very much interested in more this type of exchange. But I do admit I have quite little, at the moment, you know, impact in terms of that. I mean, our group has been really basically just doing the work, and then I think it has been, you know, it's picked up. It's been picked up by people, surely also in the kind of policy. But I couldn't, you know, really argue that, you know, that there was a direct, you know, effect. But, you know, as I said, if you look from the past, you know, with lead isotopes, there was really, you know, a direct input of, you know, effect of, you know, non-leaded gasoline. So I think there is an effect.
Saying that, let's not forget that we are talking about different countries here. Transboundary pollution is a very, very hot topic because it's involving several legal systems that at some point need to get in agreement, if that is possible. But anyway, ¿alguna otra pregunta? Jaime.
Yeah, before Jaime asked, I was just thinking something similar as he asked. Maybe it would be possible to install a permanent program at different places where has been known. For example, once I've heard that a thermoelectric plant at Hidalgo generated a lot of, I don't remember what was the metal, but some metal that it took this metal maybe 2 days to arrive to Greenland. So maybe if a permanent program was installed at some important places, you could create some kind of policy program just to, I don't know, try to avoid or to help the places where lead, for example, are creating some health issues on the population.
Yeah, I mean, I guess it's a very good question. I mean, partly, I guess I was kind of too young for that, but then, you know, in Europe, obviously, transboundary pollution is really a big problem because the countries are just so close to each other. How far, I guess, you know, kind of, you know, attributing, you know, I just know that there were quite a lot of, you know, kind of the Norwegian said all the pollution comes from the English said, you know, all the pollution comes from, and, you know, there are obviously atmospheric models which try to, you know, to pick that up, which, you know, are maybe less and more or less successful. I guess, I mean, ultimately, at least, again, you know, it's really probably out of depth, but it seems that in Europe, ultimately people just realize, well, you know, we're all contaminating, you know, and somehow, you know, obviously there live more people in Britain than in Norway, so, you know, so just everyone has to put the efforts and, you know, reduce, and then that's what happened, and I guess, you know, the overall emissions, you know, plunged down. I guess if, you know, as a tracking down and, you know, I mean, in terms of, as I said, pollution of general areas like the North Atlantic, I mean, for the lead, you know, we clearly can say that the Americans polluted it. But then again, you know, it's the open ocean, so who's responsible for the open ocean? And having said that, you know, I think, you know, the Americans then put together their act actually much earlier than the Americans, the Europeans. And I mean, the Americans just had bad luck because obviously the westerlies bring just everything, you know. It's not that, you know, the Europeans were better, but it's just the atmosphere brought it, you know, from west into the Atlantic. So I guess it's ultimately, I mean, I personally would probably argue, rather instead of saying, you know, you are the bad, you know, you're the bad, or, you know, just accepting, you know, we are developing as a society, we are creating dirt, and we just, you know, as you know, together we just try to solve it. You know what I mean? And as I said, you know, just there are more Americans than, you know, and there's the atmospheric circulation. Yeah, they produce more, okay, and, you know, obviously we should tell them to cut back. But then, as I said, similarly goes now for the Chinese. I mean, it's probably a rat race. You know, now the Chinese probably have, and the Indians have now to, and the Brazilians have, you know, to start. To put their act together. Having said that, I mean, although that's something we're still writing up, but we just did a study where we looked at the Southern Atlantic waters, and there seems actually quite little effect of, for example, the Brazilian economy on the South Ocean waters, which is quite interesting. So we're kind of expecting, you know, that we get increased concentrations. We looked at arsenic, lead, and antimony, because they're very volatile elements, but couldn't see anything. So kind of they're quite amazing results, actually. So I was surprised about that. So I guess, you know, on the bottom line, I guess, you know, on one hand, you know, we have to just go on in monitoring, which I agree with you, and testing. But then I guess also have the attitude, you know, it's one big planet, and we all sit in the same planet. So, you know, instead of, you know, just looking who's the culpable, you know, we just say, well, we all want to have a nice car and a nice TV at home, so, you know, so somehow we just all have to find together a way that, you know, to solve that problem. I mean, I said I'm not the policy person, so I'm talking more about my personal.
Do you think there will be more precise techniques than this mass spectrometer?
I mean, it will. I mean, as I said, I mean, our group kind of has been working now on these isotope systems as kind of a novelty. With zinc and copper, as I said, I mean, I didn't show the results. We think there are some promising results. Yeah, I guess, you know, it will, I'm sure, you know, we will go on and on. But I guess the big issue is obviously often economical in terms of just, you know, how much it costs to make this analysis. And I think that's you know, we tried different ways, you know, to measure lead isotopes much cheaper. explored 2-3 avenues, but they're still, you know, more expensive than probably an average consultancy firm would spend on an environmental assessment. From that point of view, I guess you get then at the point, like, you know, like in medicine, I guess the more sophisticated the technique is, the more expensive it is. You know, are you then willing to pay for that, and who's willing to pay for that? I guess that's one of the open questions. But I mean, you know, analytically, technically, surely, you know, developments go on, and, you know, that will, as I said, I think, you know, the precisions, I said, which I showed for the lead isotopes, you know, compared to, you know, probably Gabriela measured when she did her PhD, you know, it's order of magnitudes already better, you know, so, and there's been a development.
Hold on there.
It was just not as good as an instrument, but it's been, you know, 10 years, so, you know, there will be development, hopefully, and that, you know, will improve, but as I said, the methods which we use, you know, at the moment, they're far too expensive that any normal, probably, environmental assessment group would use it, you know, for anything.
¿Alguna otra pregunta?
Yes, do you think biofuels is a better alternative than gasoline for things like
I mean, I'm not the person to make a comment, because, I mean, that's simply something I don't know. I mean, I got just really involved because we wanted to look, as I said, you know, I mean, ultimately it's always I mean, from the energy point, I simply can't comment. From the pollution point of view, I mean, it's always, you know, a simple mass balance, you know, thing. So, you know, how much you're burning, how much is initially in biofuels. I really don't know, you know, what kind of the average trace element concentration would be in biofuel versus gasoline versus unleaded gasoline. I just simply don't know. Clearly, what the Brazilian study showed is, you know, unleaded gasoline is not unleaded, you know. There's not additional lead which is put into the system, but there is, you know, trace elements just by the production process. Given the whole, you know, the sheer big amount of gasoline which is used, even if it's unleaded gasoline, you know, it will pump massive amounts of lead into or I mean, massive, as I said, I should be careful because I did never do a mass balance. But obviously, in that case, you know, the kind of the colleagues at USB, they approached us and said, you know, would you be interested in such a study, because they knew that we can measure it so good. So we got involved in that, but I would actually have to refer probably again, you know, rather to, you know, places like what you do, because you probably have much more information about, you know, how much people, you know, emission numbers and all that, you know, and concentration. That's something I haven't been, you know, dealing with. So as ignorant as it sounds, but I guess our participation in this USB program was really just to measure the lead isotope, to show, you know, there's clearly from the isotopic point of view, there is very little lead coming from biofuel. Having said that, again, you know, if you obviously there's an increased use of biofuel, that might then change the whole, you know, mass balance quite quickly. So you have to do obviously also proper mass balance, which in that case, I assume the colleagues at USB did, so that's something which I wouldn't know. But yes, I mean, I guess it's certainly something, you know, which people have to take into account. And it was just another, which we're working at the moment, which is quite interesting. We're also interested in the effect of oil pollution on, you know, on the ecosystems, on the marine ecosystems. And if you think, you know, when there's an oil spill, obviously we often think it's just the oil which is, you know, making the damage, but the concentrations of trace metals in oils are extremely, you know, can be extremely high. I mean, you know, several thousand ppms, which of course, if it's in the open ocean, you know, if you do the calculations, I mean, that's luckily a drop in the ocean, literally. But obviously, if some oil spill happens in a confined area or something like that, you're actually pumping massive amounts of toxic trace elements, which we don't think of, because we think first, oh wow, it's the oil spill, so the oil makes the damage, which is probably the most immediate damage. But you know, you have to. It's ultimately the masses, and if you think then on the bigger picture, you know, well, hang on, maybe there's little trace concentrations in the biofuels, but if we start to use large amounts of biofuels, you know, then it becomes an important factor. So that's, as I said, I mean, I'm not in policy, so I don't do these kind of calculations, which I guess, you know, people like you, obviously, you're much more in a place to do that. But my feeling is, you know, that would be something important to look at. Certainly in even in the form of a master thesis or something like that. There's very simple guess mass calculations you can do, but I guess there would be, I'm pretty sure there will be very interesting things come out, you know, where you can already get an idea, you know, well, hang on, you know, what danger is, you know, associated with it.
Tiempo para una última pregunta.
I mean, I personally, not to be honest, I'm aware of, but then again, there are some names which I know from Arizona. There's a guy, Michael Ketter is his name. He did a lot, I don't know, but he did definitely lead isotope studies along the border, US, Mexican, looking at the sources, for example, of the lead, you know, what's the main sources of it, and, you know, what's the effect, how far he went just to look at industrial complexes. I really am not aware. I mean, I would have to look in the literature, but surely I know that's a person at Arizona State who's actively looking into that from the trace element and isotope point of view. When I talked with Gabriella, it seems like that, you know, there's a lot of work going on here as well. I think it's, you know, obviously it's very, you know, powerful technique, you know, if there is, you know, like there is an interest, you know, to look in, you know, the trace element, like contaminate, like lead fluxes, you know, coming from these from these cars and things like that. I know definitely that people, at least in the US, and I guess I'm sure also in Mexico, looked at this, you know, at the potential, you know, fluxes of these toxic elements using isotopes. As I said, I know this one name, which, you know, if you're interested, I'm happy to give you his address, and, you know, maybe, and he has been involved in, you know, kind of Mexican-US joint proposals that I know. I'm pretty much sure of that. What the results exactly are, I wouldn't know. Yeah, but I think, yeah, I guess that's something of the very, you know, important questions. And I'd argue, as I said, you know, isotopes, lead isotopes, and also other isotope systems, like probably nitrate or something like that, nitrogen can do a lot in that case, but it would be very important to do that, I'm sure. Yeah.
Bueno, pues ¿qué pasó, Jarama, no? Muchísimas gracias por su presencia, muchísimas gracias, Dominik.
Thank you.
Y bueno, despidámoslo con un aplauso. Gracias.